Welcome. This will be a video lecture on Section 2.6, Two Quantitative Variables, Linear Regression. Now this Section 2.6 ties in very nicely with the material from Section 2.5, so make sure you have a firm grasp on all that material from Section 2.5 before you watch this lecture. I've taken this Section 2.6 and I've broken it up into 4 subsections. We'll start with an example, then we'll talk about exact linear models, and then we'll talk about the regression line, and we'll wind it up with a discussion of residuals. So let's begin with an example. Using StatKey, load the file descriptive statistics and graphs, two quantitative variables, NBA players -2E, defensive rebounds versus offensive rebounds. This is a file we've looked at before. I think you'll see that it should be very familiar to you. Now our goal is to build a linear model that allows us to predict a player's number of defensive rebounds from their number of offensive rebounds. In other words, the explanatory variable in our model is going to be the number of offensive rebounds, and the response variable is going to be the number of defensive rebounds. So let's take a look at that file. Now we've seen this file before, we've worked with it, but let's just remind ourselves what's going on here. Each one of these dots represents an NBA player. When you put the mouse over the dot, what you're seeing is the number of offensive rebounds, that's the number on the left, paired up with the number of defensive rebounds. This is the scatter plot for those two quantitative variables, offensive rebounds and defensive rebounds. Now what we're going to try to do is fit this data with a straight line. You can see that the data does not fit on a straight line naturally, so we're going to do the best we can to draw a line through this data. And then we're going to use that line as a simple predictive model that says, if I know the number of offensive rebounds, I can plug into the equation of this line and make a decent prediction for the number of defensive rebounds. Now, that's the goal. What I want us to do is go back to the class notes now, and we'll take a look at some of the things that we'll want to discuss in solving this problem. So in building our model for NBA rebounds, our first task is going to be to draw a line through the scatter plot that fits the data. Now I say fits the data because it's not going to be a perfect fit. We're going to just try to do the best we can by using our eyeballs, okay? Step 2 is going to be to determine the equation of this line, and we're going to put it into slope-intercept form. Typically this is done by trying to find a couple of coordinates that the line passes through. Then we can quickly find the slope of the line and we can put it into slope-intercept form. We'll take a look at that in just a second. Now we want to look at part 3. Suppose a player has 252 offensive rebounds. Use your model, your line, to predict the number of defensive rebounds for this player. So we're going to put the model to use in a specific case where a player has 252 offensive rebounds. Finally, one NBA player had 220 offensive rebounds and 699 defensive rebounds. What would your model predict for this player? So knowing that they had 220 offensive rebounds, what would you have predicted for their number of defensive rebounds? And let's answer this question. How far off is your prediction? That's what's called the residual, and that's a very, very important quantity in constructing these linear models. So we're going to look at that question of the residual in that context. Now, we're going to try to answer these 4 parts in the context of that scatter plot that I showed you. And we're going to work this using the overhead camera. So join me over there, and we'll work through these 4 parts on the overhead camera. All right, welcome to the overhead camera. I've printed out a copy of that scatter plot for the NBA data. And remember, our first task, the very first thing we're supposed to do is draw a line through the scatter plot that fits the data. Now, I've got a ruler here. I'm just going to kind of move it around here until I find what I think is a good fit. I want to make sure that I've got, a balance, some of the data above and some below. I'm just going to eyeball it. And there's my straight line that I think fits the data fairly well. All right, now, determine the equation of this line and put it in slope-intercept form. Now, one way to do this is to find find the coordinates of a couple of points on the line, and it helps if you kind of keep them pretty far away from each other. Don't pick points that are too close to each other. Now, I'm in luck in this case because I have an intercept that I can read, and that's going to be very helpful in this case. That's at 0, 100, so that's 1 point on the line. And then there's another point on the line way up here that's pretty convenient, and that's at 350 paired up with, it looks like 800. Okay, now we want to put this the equation of this line in slope-intercept form. Let's get the slope. It's going to be 800 minus 100, the change in the y-coordinate, so to speak, over the change in the x-coordinates. Now 800 minus 100 is 700. And 700 divided by 350 is 2. So this line has a slope of 2, which is pretty convenient. It also has an intercept of 100. So our equation is in the form y equals 2x plus 100. Now, we want to try to keep this in some natural variables here. Remember, our input variable is offensive rebounds. We're going to use O to denote the offensive rebounds. And our output variable is defensive rebounds. Typically, we would use O and D. Now, in the context of working with these models, these linear models, it's very helpful to notate the output variable slightly differently than you would the variable for the data itself. So if we're using D to denote the defensive rebounds, I'm going to use D hat, D with a hat on top of it, to denote the output of this line. So my equation is going to look like this. D hat is equal to 100 plus 2 times O, where O is the number of offensive rebounds. I'm going to put that in parentheses just so I don't think of that as a 0. All right, so I'm going to take my offensive rebounds, multiply them by 2, and add 100, and that's going to be my predicted number of defensive rebounds. All right? Offensive rebounds times 2 plus 100 is my predicted number of defensive rebounds. Let's put this to use. So, suppose a player has 252 offensive rebounds. Use your model, your line, to predict the number of defensive rebounds for this player. So let's say we want to do that kind of calculation. So what are we going to do? We're going to take our 252, that's our number of offensive rebounds. We're going to multiply it by 2, and then we're going to add 100 to that. Now, 252 times 2 is going to be 504. And so we would predict that this player with 252 offensive rebounds would have 604 defensive rebounds. Now, we're using the hat to say that that's a predicted number of defensive rebounds. We're not saying that they actually had that many defensive rebounds. We're just saying that that's a predicted number of defensive rebounds. Okay? One NBA player had 220 offensive rebounds and 699 defensive rebounds. What would your model predict for this player, and how far off is your prediction? Now, I've put that element here. That's that player right there. 220 offensive rebounds and 699 defensive rebounds. So I've indicated them there in a black dot as opposed to the red dots for all the other data. What would our model predict for that same number of offensive rebounds? So let's do that calculation. So D hat in this case is going to be the 100 plus 2 times 220. And that's going to be 100 plus 440, or a predicted 540 540 defensive rebounds. Now, we can see this in the picture, right? If I'm plugging in 220 offensive rebounds, if I'm plugging that into the line, there's the predicted number of defensive rebounds, right? It's going to predict this dot. It would say for the 220 input offensive rebounds, I would think the defensive rebounds would be here. In fact, this player had far in excess of what the model would predict. So it's sitting at 540 as a predicted number of defensive rebounds, and this player far exceeded that. He had 699 defensive rebounds. So what we want to calculate now is this gap. The gap between what's predicted and what actually occurs in the data is called the residual for this data point. So this is called the residual. It's the residue, if you will. And the residual in this case is going to be the 699 minus the predicted 540. And so that particular data point has a corresponding residual of 159. There's 159 additional rebounds that were not predicted by the model. So the model predicted 540. There's another 159 that are unaccounted for by the model. So the model only gets you so far. And that's very typical. It's often the case that your scatter plot is not going to fit a line nicely, and so you're going to have residuals all over the place. No matter where you draw your line, you're going to have residuals, okay? And the idea of finding a good fit means you're minimizing those residuals. We'll talk about that as we get deeper into this, but the idea behind a line that fits the data well is that it tries to keep those residuals as small as it possibly can. Okay, I want to go back to the class notes now, and let's talk briefly about exact linear models so that we can talk intelligently about these inexact linear models. Okay, so I'll meet you back at the class notes. Let's take a look at a problem that involves an exact linear model. This will help us understand a little bit better what's going on when we study these inexact linear models. So, Al wants to install some natural stone tile. He calls Acme Tile for a quote. The receptionist is in a bad mood. He tells Al, to install natural stone tile, it costs $1,510 for 200 square feet and $3,610 for 500 square feet. You can figure out the rest for yourself. Find the equation of the line that predicts the cost of installation from the number of square feet of tile installed. You may assume a linear relationship between the variables. So we'll assume that there is an exact linear relationship between the number of square feet of tile to be installed and the cost of the installation. We'll look at two follow-up questions. What is the meaning of the slope of this line? And what is the meaning of the intercept of this line? We're going to go over to the overhead camera and work out these problems. So join me over there to see the solution to this problem. Okay, so let's take a look at the information that we've been given. We know that to install 200 square feet of tile costs $1,510, and to install 500 square feet of tile costs $3,610. Now, here's the first and the most important thing that we want to get straight when we're working this problem. We have to understand which of these variables, the square feet of tile or the cost of installation, which of these is the explanatory variable, which of these is the input, and which of them is the response variable or the output. Now, the way that we're thinking about this problem is we're thinking of using the number of square feet as our input, and from that trying to generate the cost of the installation, so that'll be our response or our output variable. So we're going to think of this as x and this as y, where x is equal to the number of square feet of tile to be installed. That's our input. And our response or our output is going to be the cost of installing. the tile, right? So y is going to be our cost in dollars, and x is going to be our area of tile to be installed in square feet. Okay, now once we have that relationship set up, what we should do is we should think of these, therefore, as ordered pairs that are situated in the plane. And what we're trying to do is figure out the equation of the line that passes through those 2 points. All right, so this is this first point, and here's that second point. Find the equation of the line that passes through those 2 points. Now, this is a fairly straightforward exercise. We're going to use the coordinates of these points to find the slope. So we'll look at the change in the y coordinates divided by the change in the x coordinates. And when you work that out, you get the number 7. All right, so I've set this up so that the numbers work out fairly nicely. We get the number 7. And then the next thing we have to do is we have to find the intercept. We want to write this in slope-intercept form. That's very common in this context. And so we know that our line's going to have the form y equals b plus 7x, where b is the y-intercept. Now we can simply take one of these points, it doesn't matter which one, and we can simply plug it in and solve for the unknown b. So plugging in this first point, we get 1510 equals b plus 7 times 200. 7 times 200 is 1400. So we can see that b is going to be the 1510 minus the 1400, or 110. So let's go over here and write down the final form of the equation of our line. We are going to have 110 plus 7 times x. Okay? Now, if you're in doubt as to whether or not you've generated the correct equation for the line, one thing you can always do is plug your 2 points in and make sure that they both fit on this line, because these were the points that were used to generate this line. So by plugging these points in, you should get equality. So check if you're in doubt. Okay, but I think we've worked fairly carefully here, and I think we've got the right equation for our line. All right, so what we could do with this line now, of course, is we would know, depending upon how many square feet of tile we'd want to install. Let's say I've got 1,000 square feet of tile that I want to install. I can simply plug into this relationship now and generate the cost of that installation. Fantastic. Now, what do we want to do now? We want to know, we're asked to find the meaning of the slope of this line. So what does that 7 correspond to? All right, so one way to think about the meaning of that number 7 in this context is as follows, right? For each additional square feet of tile that I want to install, right? For each additional square feet of tile I want to install, the company is going to charge me an additional $7. So this is basically the charge for each additional unit of tile, square foot of tile that I want to install. So let's imagine that we've contracted this company, Acme Tile, to do the installation for us. They show up, and I realize that there was a closet that I wanted the tile installed in, and this closet had 10 square feet of tile, or 10 square feet of area in it. I can quickly know that the cost to me is going to be $7 for each additional square foot of tile. So I would know that those 10 square feet are going to cost me an additional $70. All right, so that's the idea behind the slope. All right, that's the cost for each additional square foot of tile. What is the meaning of the intercept, this 110? What is the meaning of the intercept for this line? Well, typically you can find the meaning of the intercept by imagining what does it mean for this input variable to be 0. So what this is saying is that even if I want 0 square feet of tile installed, I've already incurred a charge of $110. All right, and you can think of that as what's usually called a fixed cost. That's just the cost to have the workers load up their truck and with gas and load it up with the tile to be installed and the other things that they would need, and just come out to your place to do the work. So there's already kind of a cost that's built into the work before a single tile is installed. So when we're building these linear models, we're going to want to pay special attention to the meaning of the slope and the meaning of the intercept. So let's get in the habit of building these linear models and kind of thinking about, in the context of the problem, what is the meaning of the slope and what is the meaning of the intercept. Okay, so let's go back to the course notes and keep working our way through this material. Regarding the previous problem, we say that there is an exact linear relationship between the number of square feet of tile to be installed and the cost of installation. In other words, once I know how much tile is to be installed, I know exactly how much it's going to cost me to have that tile installed. Now, in truth, the relationship between the number of square feet of tile to be installed and the cost of the installation is never going to be this simple. Anybody who would price a job this way is probably not going to be working for too long, because people who install tile for a living know that a lot of the work in installing the tile is all of the cutting that you're going to have to do. So if you come into a space that's going to require lots and lots of tile to be cut and fit precisely, that's going to be very time consuming and that's going to be costly. So in fact, even this relationship that I've articulated in this problem is a little bit too simple. And in fact, that's the way life is in general, right? In fact, we never really have perfect linear relationships between pairs of variables. Now, let's go back to our problem that we started with, just to show you how difficult this is, right? We're trying to use the number of offensive rebounds that a player's had to predict their number of defensive rebounds. Think about how hard this is. Think about why this relationship is probably far from exact, right? In fact, both of these rebounds are highly influenced by some other confounding variables, by some other variables that are not present in the problem, right? So think about the things that influence both offensive rebounds and defensive rebounds, right? The size of the player is important. What position do they play? Are they playing a forward or a center position? Are they near the basket typically, or are they far away from the basket? That's going to affect the number of rebounds. How much skill does the player have, right? Because I can take a person off the street with the same size and position as a great NBA player, but they're lacking the skill, and they're not going to be able to rebound nearly as well. So the skill, the desire, right? Rebounding just takes a lot of desire. It takes a lot of competitive spirit. So that's another thing. And not everybody has the same amount of competitive spirit. So that's another factor that's in here. Your team actually plays a large role in especially your number of possible offensive rebounds. Think about this. If you're on a team that shoots the ball really, really well, the number of offensive rebounds for you that you can get is actually going to be less. If you're on a team that shoots the ball very poorly, you're going to have many more opportunities for offensive rebounds. So there's kind of a hidden variable there, which is your own team's ability or inability to shoot the ball. Now, you can start imagining all the other factors that are going to impinge on both the offensive rebounds and the defensive rebounds. And some of these factors don't impinge on these variables in exactly the same way. And so you're going to start to see some inexactness, right? You're going to see that the number of offensive rebounds will not perfectly predict the number of defensive rebounds. It's a very fuzzy problem. Yet, these two are, in some sense, related to each other, right? So there is the possibility, at least, to construct a model that allows us to predict the number of defensive rebounds from the number of offensive rebounds, at least with some accuracy, all right? So it would be better than nothing. And that's what we're going for here. We're going to try to squeeze out as much information from the data that we can to make the model of predicting defensive rebounds from offensive rebounds at least as good as it possibly can be. All right, but hopefully you understand the difficulty that's inherent in this kind of problem. All right, now here's the big question that's looming and this is what we're going to be studying for the rest of this section, is suppose we have some paired data. So think of this as a scatter plot. How can we create a linear model for prediction in the presence of inexact data? So when we have inexact data, data that does not already fit on a line, how can we accurately build a model, or build a model as best we can, to make predictions in the presence of this inexact data? And that leads us to the topic of the regression line. The process of fitting a line to a set of paired data, a scatter plot, is called linear regression. The line of best fit is called the regression line. Now, I think one way to get into this is just to look at some paired data, a scatter plot, in StatKey, and use StatKey's built-in regression line calculator. That way we can study some aspects of the regression line without worrying about how that regression line is actually formed. So let's head over to StatKey and look at some data. Now, the particular problem I want us to study is a data set that we've looked at before. So we're going to load StatKey. We're going to go to descriptive statistics and graphs, two quantitative variables, cricket chirps, temperature versus chirps. We looked at this data set already. If you remember, these observations are pairing the number of beats per minute with which a cricket is chirping with the ambient temperature. Okay, now on the scatter plot controls, we're going to select Show Regression Line. And that's going to show us the line of best fit for this data set, for this scatter plot. Question 1, what is the equation of this line? I'll show you how we can get the slope and the intercept right out of the summary statistics in StatKey. Is this an exact fit? Well, we'll know once we see the regression line. In the data set, 123 chirps is paired up with a temperature of 67.5. For 123 chirps, what temperature would the model predict? And for that paired data point, 123, 67.5, let's calculate the residual, where what is the residual? It's the actual temperature, it's the actual data point, minus the predicted. So in this case, that'll be the actual temperature, the actual ambient temperature that was registered with this data point, that's the 67.5, minus what the model would predict. Okay, now let's go over to StatKey. We'll load this data file and we'll work our way through these four parts. So let's take a look at that data set. We're going to load the file called cricket chirps, temperature versus chirps. And this is a data set that we've seen before, but let me just remind you of what the context is here. There were a total of 7 observations made, and for each observation, there was a cricket chirping. In this case, this one that I've highlighted, there is a cricket that's chirping at 150 beats per minute, and the ambient temperature is 72 degrees. So each of these points in the scatter plot is pairing a beats per minute chirp rate and the ambient temperature. Okay, what I want to show you though, and this is new, is there's this box here that we can check. If we check this box, StatKey will show us the line that best fits that data. This is the so-called regression line. And if we want to know the equation of that regression line, we can go to the summary statistics and read off the slope and the intercept right here. So that red line that we're seeing has an intercept of 37.679, and it has a slope of 0.231. So we have 4 tasks with this problem. We want to know what is the equation of this line. Now, I would pick some variable names that are meaningful here. So let's let T be the temperature. And so I'm going to call T hat the predicted temperature. So T hat is going to be equal to, and I'll use C for the beats per minute for the chirp rate. So I'll use C for the chirp rate. So I would say T hat is going to be equal to 37.679 plus 0.231 times the value of C. To put it another way, if you hand me the chirp rate, I'm going to simply multiply that by 0.231. I'm going to add on 37.679, and that's going to give me T hat, which is the predicted temperature that corresponds to that chirp rate. Okay, so that's the equation of the line. Is this line an exact fit for the data? It is not. You can see that these points, some of the points lie above and some of the points lie below the red line. So obviously the line is not an exact fit. It's a pretty good fit though. So we have to say that it does look like the chirp rate is a fairly good predictor for the temperature. All right. In this data set, 123 chirps is paired up or paired with a temperature of 67.5. We can see that point right here. There's one of our observations. Okay, for this same 123 chirps, what temperature would the model predict? So we have to imagine that we're going to be plugging 123 into our red line. It's going to give me a corresponding value of T hat, which is the temperature that the model would predict for 123 chirps. Let's get the value of T hat. Now remember, we're working with an input of 123 chirps, and our slope and our intercept are given by 0.231 and 37.679. So let's go over to the scientific calculator here. Remember, I'm going to take my 123 chirps that's given. I'm going to multiply that by the slope, which is 0.231. And then I'm going to add to that the intercept, which is 37.679. And what this tells me over here, I can see that the predicted temperature for 123 chirps will be 66.092 degrees. And remember, the actual value, the observed value, was in fact 67.5. Okay, final question. For the paired data, 123, 67.5, so in other words, for this particular point, calculate the residual, where by the residual we mean the actual value for the temperature minus its predicted value. Now geometrically, the residual is going to be the gap here between the predicted value, which is going to sit on the red line, and the actual value, which is here. So in this case, the residual is going to be a positive value because our actual point is above the line. This point over here will have a negative residual. And you can see that anytime you have a line of best fit, you're going to have some negative residuals, points that lie below the line, and some positive residuals, points that lie above the line. In fact, one of the features of the residuals is that collectively the residuals should add up to 0. In other words, there's always going to be this balance between the positive residuals and the negative residuals to give us a net 0. But let's stick to this problem in hand. We've got the 123 chirps, we've got the actual temperature, and we've got the predicted temperature. Now we want to calculate the residual. That's fairly easy to do. Let me give myself a new line here. All I have to do is take the actual temperature, so we always go actual first, minus predicted, and it's still here for us to see, 66.092. And the residual is over here. It's 1.408. So we're off by 1.408 degrees. So we're underestimating a little bit. We would have to take our estimated value or predicted value, and we'd have to tack on another 1.408 degrees to get up to what was actually observed that day. Okay, so hopefully that gives you some sense of how StatKey can take a scatter plot, and by clicking on Show Regression Line, we can see the regression line in the scatter plot, and we can pull this information, the slope and the intercept, right out of the summary statistics, and we can get working on using this predictive model. Also, we studied the residual, which is the difference between the actual value and the predicted value. All right, now let's go back to the class notes. I want us to look at the interpretation of the slope and the intercept in context. Okay, so let's take a look at that topic. So consider the regression line y hat equals a plus bx. So x is our explanatory variable, and we're using x to make predictions for a variable called y, and we're calling those predicted outputs y hat. Okay. The slope b, represents the predicted change in the response variable y given a 1 unit increase in the explanatory variable x. So in other words, if x changes its value by 1 unit, then we will see a corresponding change in the predicted value by b. So b is going to be the predicted change in y given that 1 unit change in x. We're going to look at a concrete example in just a second, so let's just read through this and then we'll try to put this in the context of a specific example. Now the intercept a, on the other hand, represents the predicted value of the response variable y if the explanatory variable x is near 0. And this interpretation is not always reasonable in context, so you'll have to be careful in interpreting the intercept because having the explanatory variable near 0 may not make a lot of sense. So let's take a look why this is the case, though. So imagine that this input variable x is set equal to 0. So this product is equal to 0, and this just says the predicted value, therefore, is y hat equals a. So we can think of a as the predicted output if x is equal to 0. Okay, let's see what this means in the context of the example we just studied, right? So what are the interpretations of the slope and the intercept in the temperature versus cricket chirp model that we just studied? So we just looked at this example using StatKey, and we saw that the predicted temperature could always be obtained by taking the cricket chirp beats per minute, multiplying by 0.231, there's the slope, and adding on the 37.679, that's our intercept. So what is the meaning of the 0.231? It means that if the crickets were to chirp one more beat per minute faster, in other words, if the beats per minute went from 125 to 126, or 126 to 127, if the beats per minute went up by 1 unit, we would see a rise in the temperature, or at least the predicted temperature, by 0.231 degrees. And so this is telling us how much of a change we're going to see in our predicted temperature with an extra unit of increase in this input variable, in this case, the cricket chirp beats per minute. What's the interpretation of the 37.679? It would say something like this. If the cricket chirp beats per minute were 0, if we weren't hearing the crickets at all, we would predict an ambient temperature of 37.679. Now, there are several problems with this interpretation. You can imagine that the crickets, you might not be hearing the crickets because there aren't any crickets around to be heard. Another thing is we don't understand the behavior of crickets. Maybe once the temperature reaches a threshold, they just stop sounding at all. We don't hear them chirping at all. So it's not clear that we can extrapolate through this model, through this predictive model, all the way down to cricket chirps equaling 0. So we have to be a little bit careful in trying to put too much meaning on the 37.679 in this case. All right. Our next topic is residuals. This is our last subsection within section 2.6, and it is our most technical section. The residual at a data value is the difference between the observed and predicted values of the response variable. We've seen a couple of calculations of residuals already in section 2.6. On a scatter plot, the residual represents the vertical deviation from the line to a data point. Points above the line will have positive residuals, and points below the line will have negative residuals. If the predicted values closely match the observed data values, the residuals will be small. In a sense, this is the definition of the regression line. It is the line that squeezes out all of the efficiency that is possible. It makes the residuals collectively as small as they possibly can be. Now, I think it will be helpful for us to take a look at an example to get the picture of the regression line, the scatter plot, and the residuals into our heads. In this figure, the scatter plot is represented by the red dots, and the blue line is the regression line. The residuals are being indicated by these vertical bars. Now let's think about how we're supposed to think of these residuals. So for instance, let's take a look at this point here. What is the residual at that point or corresponding to that point? Well, we begin at the predicted value on the blue line, and then in this case, we have to work our way down to the data point. That is a negative directed distance, and that is a negative residual. For this data point, however, we begin at the blue line and we find ourselves working up to the data point. That is a positive directed distance. That's a positive residual. Now, one of the features of a regression line is that it always balances the residuals. In other words, the sum of the residuals will always be 0, and that's why in any regression line, right, unless the data is fitting perfectly on the line, in any regression line you will always have some of the data spilling above the regression line and some of the data spilling below the regression line. There will always be some positive and negative residuals. They will balance each other out. Now, more than that though, let's take a look at the technical definition of what the regression line actually does. All right? The regression line is the line that minimizes the sum of the squared residuals. Let me say that one more time. The regression line is the line that minimizes the sum of the squared residuals. That's what the regression line is doing. It is squeezing out efficiency. It is making the residuals as small as they possibly can be in this sense, that the sum of the squares of the residuals are as small as they can possibly be. Now, the regression line is very, very important, and it is known by other names, and so you should be aware of this, right? That the regression line is also called the line of best fit, or the least square line. It gets that name from this this property of the regression line, that it's minimizing the sum of the squares. So it is the least square line. Now, hopefully, this will all make sense once we work through a regression and residuals handout. So I want to work that with you on the document camera, and by the time we're done, I hope you'll have a better appreciation for how this regression line is formed and what it's doing. So join me at the document camera to work through this handout. All right, so welcome to the document camera. We're going to work through this regression and residuals handout, and hopefully by the time we're done with this, you'll have a much deeper appreciation of regression lines and residuals. Now, the question that's motivating this study is this: can we predict the weight of an NFL player from his height? So can we build a predictive model that says, once I know the height of a player, I can make an accurate prediction of the weight of that NFL player? So to help us develop a predictive model, 7 NFL players were selected at random. The pairings of their height, which we'll call H and it's measured in inches, and weights, W, measured in pounds, are given below. So here are 7 ordered pairs, and in each ordered pair we have an NFL player's height in inches and weight in pounds. And the scatter plot for this data set is sitting here. All right, we're going to use that scatter plot in just a second. Let's go to the questions, right? So first, we're going to build the model. Using a ruler, draw a line that you think best fits the data, or fits the data best, and then find the equation of your line. And then express the equation of your line below by filling in the slope and the intercept of your line. So our predictive model is going to be of the form: predicted weight is equal to some intercept plus some slope times the height. All right, so let's go ahead and go back to our scatter plot. All right, we're going to want to use our scatter plot here to help us find, guess a line of best fit. So I'm going to kind of poke around here a little bit, and I'm going to kind of just look and just say, all right, that looks like a decent line that fits the data. Okay, so I'm going to use that as my line, my purported line of best fit. Okay, now, one of the things we have to do is work out the slope and intercept of this line so that we can build the equation of this line. And one thing we can do to help us in this endeavor is to find a couple of points where the line is passing through. So here's one. And let's say up here is another one. So let's get the coordinates of these points. So that point up here, each one of these grid lines is a 1, so that's going to be at 76, 77, 78. And it's paired up with 300. So 78, 300 is one of the points on our line. And down here, I found a grid point that's going to be at 70. And let's see, 190, 180, 170. Okay, so let's take this information with us to the next page. We have our 2 points. $78, 300 and 70, 170. The first thing we're going to want to work out now, we'll come back to this page a little bit later. The first thing we're going to want to work out is the slope of this line. So let's go ahead and get that. So the slope is going to be 300 minus 170 divided by 78 minus 70. Okay, so what's that going to be? 130 divided by 8. That's going to be 16.25. So that's our slope. The intercept we can get by basically just saying, all right, we know that y equals mx plus b. And then we'll just plug one of our points in. We'll plug in our known slope, and we'll be able to solve for the intercept. So let's just we'll key in on this point, for example. We'll say we know that 170 has to equal what I get when I use 16.25 Okay, so let's take 16.25 times 70. We're going to subtract that from 170. And we get this very large negative number. Negative 967.5. Okay? So our predictive model is going to have the following form, right? We're going to say that if we're going to predict a player's weight from their height, we're going to use this as the intercept. And we'll use 16.25 as the slope. So here's our predictive model. I take a player's height in inches, I multiply it by 16.25, and then I have to subtract 967.5 to finally get the predicted weight for that player. So we think of W hat as the predicted weight for a player with a given height h. All right, so what is the meaning of the slope in this line? Right, so when I think of that 16.25, what is the meaning of that slope? We're thinking of that as follows. We're saying for each unit increase in height, so for each additional inch that a player is, I'm going to add on 16.25 pounds, right? So for each additional inch, the predicted weight goes up by 16.25 pounds. All right. So every time a player that's 1 inch taller shows up, we're thinking whatever that first player's weight is, that second player is probably 16.25 pounds heavier. All right. That's the prediction. All right. Does the intercept have any meaning in this context? This is one of these cases where the meaning of that intercept, at least as the equation goes, would tell us that when a player has no height whatsoever, they would have a predicted weight of a negative 967.5 pounds. Now, strictly speaking, that doesn't make any sense. So does the intercept have any meaning in context? And the answer is no. All right. Now, our next task is to fill in the table below. In each row, calculate the predicted height, the predicted weight, the residual, and the square of the residual. All right, so we're going to work our way across row by row, and in each case, we're going to use our predictive model here. So we're going to have the 967.5 plus 16.25 times h. We're going to use this equation with each of these heights to give a predicted weight. Then we'll look at the actual weight versus the predicted weight and fill in the residual. And then finally, we'll take the square of that residual. All right. What I like to do when I do this kind of problem is I'll just work my way down and just calculate all of these predicted values. Okay. So let's go ahead. When I take 76 and I plug it into this equation, let's see what we get. 16.25 times the height of 76 minus 967.5 is going to give me 267.5 as a predicted weight. Okay? Now, I'm going to continue down each time using the different height in our model to get a different predicted weight. Now, I've done this calculation before. I will just fill in the values, but each time all I'm doing is I'm plugging in a height into this equation and working out the predicted weight. So it turns out the rest of this column looks like this. I'll have 251.25. The next one predicts to 202.5. And so this one has the same height. Not surprisingly, we get the same predicted weight. For 71, we're going to get 186.25. For 78, we're going to get 300. And for 75, we're going to get 251.25. So those are all the predicted weights that come from working with these various input heights. Now, what we want to do is we want to compare, right? Here's the actual weight, there's a predicted weight. What we want to do in each of these cases is find the residual, which is just the actual weight minus the predicted weight. So for instance, in this first case, I'm simply going to take the 251 and I'm subtract the 267.5, and that's going to give me a residual of negative 16.5. I have a squaring button on my calculator, so I'm going to hit the square right away, and I'm going to get a square residual of 272.25. Okay, let's do one more. I've got a weight of 287. I've got a predicted weight of 251.25. That gives me a difference, a residual of 35.75, and a square residual, a whopping 1,278 point, let's say 0625. Okay, so obviously, if the residual is large to begin with, its square is going to be even larger, but that's part of the game. We're going to compute all of the squares of the residuals and add them up. So we can see the penalty we're paying for a large residual. If we get a large residual, we get an enormous square. All right, now I've done this calculation already, so let me just show you how the rest of the columns look, and you can try this on your own. The next residual is negative 2.5, and then it's got a square of 6.25, and then we have negative 6.5, and a square of 42.25, and then negative 0.25. This one's very small, and so I've got a 0.0625 square residual, negative 2 and 4, and negative 10.25, and the square of that is 105.25. 0.0625. Okay, so we've got our predictive model. We've got for all of our heights the predicted weights. For all of our weights and predicted weights, we have the corresponding residual, and now we have the corresponding square of the residual. And as I was saying before, anytime you're doing a calculation like this, you should see some combination of positive and negative residuals, and we have that. The residuals should add up to 0. You can check that, but the real thing that we want to calculate is the sum of these squares of these residuals. Now, I went ahead and did that, okay? I calculated the sum of these squares earlier, and when I add up all of these residuals, I get the number 1,707.937. So I'm thinking of that as my score, right? This is my way of figuring out how well did my model work. So one way to score your model is to draw your line, construct the equation of the line, work out this table, get your residuals and your residuals squared, add up the squares of the residuals, and that's your score. The goal here is to make this number as small as it can possibly be. Now, if your data is not very exact to begin with, if it's not very linear to begin with, there's a limit to how low you can make this score, but that limit is achieved by the line of best fit or the regression line. Now, it turns out I took this data and I put it into StatKey and I asked it to find the line of best fit. And when I gave this to StatKey, it returned W hat equals negative 974.636 plus 16.342 times H. So my intercept is off. I had negative 967.5, and this is a bit different. And my slope was 16.25, and StatKey finding the line of best fit found a slightly different slope. So you can see that my line is not the line of best fit. So that's clear. Now, what is the best possible sum of the squares of the residuals? So when you use this line and compute its score, you find out that the sum of the squares of the residuals is slightly smaller than what I got. So this is as small as the sum of squares could be. I can't make the score any lower than this. I achieved this score. This is the best I could have achieved. It's 1,706.89. So if you were to try this, see how well your line would work. Check your score and see how close you can get it to the best possible score. Okay, so hopefully that gives you some insight into what the line of best fit is doing. It is minimizing the sum of the squares of these residuals. Okay, that is what the definition of the line of best fit is. All right, now that brings a conclusion to section 2.6. So that is the end of chapter 2. We're finished with all of our work on descriptive statistics, and the next time I see you in a video lecture, we will be into chapter 3, section 1. I will see you then. Until then, take care. Bye-bye.